Okay, greetings once more. Let's go through the revision of measuring instruments quickly. Like we said, we don't want to make the videos to be too long. So let's do this. So we've got electrical trade theory and two measuring instruments. All right, the first thing that we need to know, what is a measuring instrument? We said a measuring instrument is a device that is used to measure the value of an unknown electrical quantity. Well, we know that the basic ones are, let me just do this. So we are going to have an ammeter, a voltmeter, and a wattmeter. I just want us to discuss those for now under this headings here. So I want us to talk about an ammeter, voltmeter, as well as a wattmeter. All right. Now, an ammeter, we know that it's connected in series. We know a voltmeter is in parallel. And we know that a wattmeter is both parallel and series. We're going to explain that when we get to it, both parallel and series. Now, on a low voltage, here is our input. Here is our, in this case, we call it the supply. And then here we have a load. So our ammeter is just going to be there. That's why we're going to draw our ammeter there. Right. The load, you can put a resistor to show a load. So, but then on a voltmeter, how do we do it? We've got V supply. And then we're going to have, remember, the same load, but the voltmeter is now going to be in parallel. That's how we connect it under low voltage. And then on a wattmeter, remember a wattmeter measures power, and power is equal to VI, which means for us to get power, we need to get the voltage and the current, which means our wattmeter must give us both measurements, which means if we have got our load there, we need to put our voltmeter here as well as our current there. Then this is a wattmeter because it must measure both. But then there's a way in which they put it. They use a winding and a winding, and then they put a circle like that. All right. So in other words, this becomes our current coil. That's where we measure current, and it becomes our voltage coil. That's where we measure voltage. Combine the two, it gives us the power. All right, this is how we do this under low voltage. Now, also under low voltage, we can say it's a direct method. We are connecting this directly, okay, directly onto our circuit. Now, let us look at a power factor and frequency meter. How do we measure? A power factor, and how do we measure our frequency? Now, a power factor meter, please go to page 205. That's where we are going to learn the diagram of the power factor meter. I'm not going to draw it here, but why I wrote this thing on its own is that a power factor meter helps us to measure power factor. Why is power factor measurement important? So that we avoid what? Low power factor. Why do we have to avoid low power factor? If you remember on chapter 1, we avoid low power factor because it has got detrimental effect. What are those effects? There they are written on page 204. Large currents are required, decreases the efficiency of a supply system or apparatus. It limits the output generators or alternators and transformers. It results to greater fall in terminal voltage. So power factor issues is both on chapter 1 as well as chapter 10. Okay, so we need to know those conditions as to what factors do we have. Now, if you look at frequency meter connection. Again, look at that figure there, because the frequency meter is the same as the please check figure 10.6. That's our frequency meter. All right, it tells us the frequency in terms of the hertz that we've got. All right, let's move on to a high voltage measurement. High voltage measurement is also known as indirect method. Indirect. Now, what do I mean by indirect? It simply says that here you are connecting directly. You can see it's directly on the line, directly on parallel, directly on lines. But the high voltage, we can't do that. Why? Because if the voltages are too high, they would tend to damage our meter. So we are going to use transformers. We're going to do this also on N3. We're going to do this, so please just keep this in mind. So we're going to use transformers. So how do we then draw an ammeter? Now, here's an ammeter. Remember, still have a load. Now, high voltage is now going to have a line neutral. Low was plus and minus. So it means the voltage is small. Maybe you can simply say low voltage DC. Yeah? For our level. You can have a low voltage also of AC, but for our level, let's just assume that high voltages, we're speaking about level neutral, higher voltages. Now, instead of having our current here, we are going to connect it via a transformer. So we're going to connect a transformer here, and then we can have an ammeter to help protect. You see, now this is how you connect an ammeter. How are we going to connect a voltmeter? Live in neutral, get the load. How do we connect that? It's going to be, we know that we are supposed to connect it here. But now we are going to take this wire and push it up there, take that wire, push it up there, and then have a transformer and a transformer. That's where you're going to have our voltmeter there. That's how we connect our voltmeter. Now, how do we connect our, indirectly, our wattmeter? Let me just make another space here. Now, our wattmeter, remember our wattmeter must have both terminals. So it's going to have a terminal like that and a terminal like that. Now, this terminal here is for current. That one there is for voltage. Let's join them. I'm going to use the red to join them. Now, remember this one must connect like this. It's an ammeter. And then this one must connect. Oh, sorry, before it touches the line, it must have a transformer. The transformer, one comes here and one goes there. That's how we connect this wattmeter. A wattmeter and an energy meter is the same thing. So when the question says draw an energy meter or a wattmeter, we'll be drawing this. It's the same thing. All right. Now, let's look at, please go through the diagrams. Please go through the diagrams. Let's look at the range extension. Now, a galvanometer, we use a galvanometer because a galvanometer is to measure weak electric current or smaller currents. So if it's measure small currents, it means it has got a small, pardon me, it has got a small full-scale deflection. What is a full-scale deflection? Is the total current that it can measure. So if this is my needle, it starts at 0 and it ends, maybe they say 8 amps, so smaller currents, or even 8 milliamps. That's how small it can go. So full-scale deflection is the highest amount that this needle can deflect to. That's why I call it full-scale deflection. Now, the nice thing about it, it has got advantages in a galvanometer. It's very accurate, uniform scale, and it is shielded against stray magnets. Why? Because it has got magnets. So the movement of a needle is protected by magnets. Even if you put another magnet there, North Pole and South Pole, it won't be able to affect the needle. because it is protected by bigger magnets. So that's why we say by shielded against from stray magnetic fields. Stray magnetic field are the magnetic fields that are not supposed to be there. All right. But it can only work on DC and it's very expensive. That's a disadvantage. Now, how can we make a galvanometer to measure higher currents? That's when we are saying now. Remember, a galvanometer is used to measure smaller currents. Now, how can it be used to measure bigger currents than that? Now, we are going to use something called a shunt. We're going to extend using a shunt. Well, we can go on and on about to show how it is done. Guys, I'm not going to go there. But that's, okay, let's do it. Here's my my galvanometer here. This galvanometer can take a current, full-scale deflection is IM, let's say of 2 amps. But I am supplying to it IL, let's say I'm supplying 10 amps, which means if this 10 amps goes to the galvanometer, it's going to damage it. So what must I do? Then I'm going to insert a shunt resistor, hence I'm saying shunt there, or shunt. Now, what does shunt do? The current is now going to split. So if 10 comes to the junction, 2 will go to the galvanometer, and I shunt will be 8 amps. I'm going to get 8 amps there. So the question is, how much must this shunt be in order to accommodate that 10? Which is not IL, actually, it's just I, total I, current. Now, how do we calculate that value of that shunt resistor? We're going to say voltage on a shunt, since they are connected in parallel, is equal to the voltage in the meter. Voltage in the shunt is I shunt times R shunt. You know V is equal to I times R. Voltage in the meter will be IM times RM. RM being the resistance of a meter, IM being the full-scale deflection. What am I looking for? I'm looking for R shunt. So I'm going to divide this side by I shunt as I divide this side by I shunt. That cancels that, which means my R shunt, will be IM full-scale deflection, RM resistance of a meter, and I shunt. This is how I am going to be calculating. Okay, right. Now, how will the questions be like? I want to go to our calculations, maybe. Let's go to number 9 on page 216, exercise 10,2. That would be number 9. What page is this? It's 216. Now, what's going to happen now? A moving coil instrument with a 5 milliamps deflection. So deflection IM, 5 milliamperes, has a coil resistance, which is the resistance of a meter, 12 ohms. Calculate the value of the shunt resistor to give full-scale deflection of 10, which means the current we are trying to measure is 10. Right, now, let's go back to this formula, the I shunt. How did we get that I shunt to be 8? We said 10 minus 2, which is I minus IM. That's how you get the I shunt, which means here we can basically remove that and say instead I minus IM. Hope that's clear. So there's the value of I and this IM, which means we can actually find R shunt by saying IM, RM all divided by I minus IM. IM full-scale deflection is 5 times 10 to the power minus 6 times, how much is RM? 12, not 6, minus 3. Minus 3. I'm thinking about the calculator. That's why I'm making these errors. Divided by I is the total current I'm trying to measure, minus the IM of 5, 10 to the power minus 3. Let me punch that on a calculator on my phone quickly. Okay. Let me punch this quickly, guys. I don't want this video to be long. 5 exponent minus 3 times 12. 10 minus 5 exponent minus 3. I'm getting Guys, please help me out here. I'm not really sure I'm using my phone, but punch that I'm getting 6 milliohms. I hope that's correct because it's 6 times 10 to the power minus 3. I hope that is correct. Please confirm those answers for me. Now let's go to the range extension, which is something called a multiplier. Now we are trying to get our meter to measure more voltage. Here we wanted it to measure more current. That's why we use a shunt. To measure more voltage, we use a multiplier. So how are we going to then go about that? So here is my meter, my voltmeter. And then here's the voltage that I'm trying to measure. Let's say I'm trying to measure 20 volts, but the full scale deflection there is 12 volts, which means if I allow this is going to break. So what must I do? I then put a series resistor, R series. This resistor is called a multiplier. Now what's going to happen? 12 volts will be there, and this one will share the what? The 8 volts, because the voltage will split in series. So now we have extended the range. It is now able to take in how much? 20 volts. But how much is that multiplier or R series? So we know that VT is equal to voltage in the meter plus the voltage in series. That's why we said 20 is our VT is equal to 12 plus 8. So this is what the statement says. But these numbers, I just put them obviously there. So VT is equal to VM is IM RM plus what is VSE is going to be I series times R series. Don't forget now, these are in series, which means that value there is the same as that value there because the current is constant, which means we can remove that and put what? IM, which means IM RM plus IM RSE. Take out the common factor there. IM RM plus RSE. I have VT. Now, I'm looking for what? Multiplier RSE. Divide by IM, divide by IM. Then I'm left with what? RM minus or plus RSE is equal to VT over IM. Then what do? Take RM across. Then I get the fact that R series is equal to VT over IM minus RM. This would be my formula to calculate a multiplier. Right, I'm just showing you where it comes from, guys. It's not so important. Maybe unless they say proof, maybe you can learn that. But let's go back to the same question. Yeah, number 9.2 now. What is our information? Don't forget we had IM full scale deflection of 5 times 10 to the power minus 3. We had R, not R series, R meter, 12 ohms. Now, we are now looking for what? We are now giving V, total voltage of 100 volts. We want this thing to measure 100 volts. So we want to find the R series. So my R series will be VM over IM minus RM, which is going to be VT is my 100 divided by my IM 510 to the power minus 3 minus RM, which is 12. Now let's get that one. Allow me also to punch it. Please confirm it with me. 100 it's a very high value. I get 19,988 kilo ohms. That's the value that I'm going to put in series in order for it to be able to absorb the extra voltage. Okay, that's how I do that. Now, if the question comes and says calculate, you must also know the diagram. You can see the diagram here. It's labeled IM, the galvanometer, or the ammeter. You can also put R shunt, just label it like that. You must know how to label it, and you must also know how to put this diagram and label it. If maybe you want to use the ones on your textbooks for the ammeter, you can check page 210, figure 1012 for the voltmeter. You can check figure 1013 for the multiplier there. Yes. All right. Excuse me. Basically, this is it that I had prepared for you. Then the theory there, please go through the theory, whereby we are talking about digital measuring instrument, because the ones we've been doing were all analog. That's why we're speaking of deflection. Now, you need to know how to use a digital instrument meter. You need to know how to use it as an ammeter, voltmeter, and an ohm meter. Which points must it be connected at? You need to know for the care and maintenance, it must always be clean. You know, advantages of using digital over analog, you must also look at that and answer those questions on 10.2. Guys, good luck. I hope that we have covered a bulk of the work that you are going to be needing, and you are going to make yourselves very proud. If you have any questions, you can go on and ask and let me know how the whole thing goes. Thank you.